Hi, this is Keshav of CSC Data Science. Today, today our topic was comparison between M-way search trees and binary trees. M-way search trees. M-way search trees are multiple search trees which are generalized versions of the binary trees, where each node contains multiple elements. In an M-way tree of order M, each node contains maximum of M-1 elements and M children. The goal of M-way search tree is of the height h calls for O of h number of accesses for an insert, delete, retrieval operation. Hence, it ensures that the height of h is close to log m of n plus 1. The number of elements in the M-way search tree of the height h ranges from a minimum of h to a maximum of m to the power of h minus 1. An M-way search tree of the n elements ranges from the minimum height of m log of m of n plus 1 to a maximum of n. An example of five-way search tree is shown in the figure below. Observe each node has its most child nodes, therefore has most 4 keys to it. The structure of a node of an M-way tree is given below. We can see there is a tree, yeah, and in the tree there are pointers to the subtree, null pointers, key fields, and here is the example of the M-way search tree. You can check it out once. Until then, I'll wait. Mhm, mhm, mhm. Okay, let's move on. Here, count represents the number of children that particular node has. The values of the node stored in array value. The addresses of the child nodes are stored in the child array. The max micro signifies the maximum number of the values at the partition node can contain. Searching in an M-way search tree. Searching for key in an M-way search tree is similar to that of the binary search tree. To search for the 77 in the 5-way search tree shown in the figure, we begin at the root and as 77, 76, 44, 18. Move to the fourth subtree. In the root node of the fourth subtree 77, 80. Therefore, we move to the first subtree of the node since 77 is available in only one node of the subtree. We claim 77 was a successful search. And here is the code for to search the value, root and position. Continuation of the code. And now let's talk about binary tree. Binary tree. Binary tree is defined as a red tree data structure which each node has at most two children. Since each element in a binary tree can have only two children, we typically name them as the left and right child. And there is an example of the binary tree where 1 is called the root node, 2 is the left child, 3 is the right child. For 2 there are two childs, 4 is the left child, 5 is the left child. For 4 there is a left and right child of 8 and 9. 5 left and right childs are 10 and 11. 6 right child is 13. 7th left child is 14. Binary tree representation. A binary tree is represented by the pointer to the topmost node, commonly known as root of the tree. If the tree is empty, then the value of the root is null. Each node of binary tree contains the following parts: data, pointed to left child, pointed to right child. Basic operation on a binary tree: inserting an element, removing an element, searching for an element, traversing the tree. Auxiliary operation on a binary tree: finding the height of the tree, finding the level of node of the tree, and finding size of the entire tree. Comparison between MV tree and binary tree. An MV tree is a tree structure that has m values and m plus 1 links. A binary tree is a special case of the MV tree with m equal to 1, meaning only one value per node and two links. If you either move down left or the right link, here's an example of the binary tree that shows this. G, 14, 20. Ah, that's all. And check the example of the binary. An MV tree that can have more than one value per node, but theory, it's still the same. You can choose which link to move down and based on the values, there's m plus 1 possible choices. An MV tree where m is 2 may look like this. These MV trees are often used in situations where you can fit more than one value in the efficient block. By efficient, I mean one that can read the written efficiently, like a disk block, sector, cluster, or cylinder, depending upon how storage subsystem operates. For example, let's say that a disk block is 512 bytes. The values of the your tree is take up to 112 bytes, and the links are take 4 bytes. In this situation, you can fix the 4 values in the disk block calculated as follows: numVals inch block size minus link size by value size plus link size in 512 minus 4, 12, 112 plus 40, 4. That gives the 4 values and the 5 links, total of 508 bytes. Although some wastes 4 bytes in this case, here is the advantage of storing an integral number that values efficiently retrievable block. Thank you.